followers, welcome back to my page. I am your officer Spy, and today's video we are going to continue with the basic aerodynamics. In last video I have covered the aerodynamic forces and moments and the aerodynamics, how it works on airfoil sections. So in today's video we are going to deal with the continuity equations, momentum equations and energy equations, and some lines and forces which fluid occurs. So in this, we are all familiar with the word called continuity equations. So in basic fluid dynamics, we all learnt what is continuity equation, what is momentum equation and energy equation. So in this basic aerodynamics, we are going in depth in that. So before going to that, we have to concentrate on some vital parts of these equations. We have to derive it and we have to see the results, how it works. And the continuity equation mainly works on the principle of principle is mass can neither be created nor destroyed. Mass can neither be created nor destroyed. So upon this the continuity equation works, and to understand this principle I am going to take a body, consider this as a body, and this is the velocity of the flow. There is some fluid flow on the body, and this is called this is the velocity of the flow, and this area of this body I will take it as a capital A. So next I will shade some parts on which fluid is flowing. Then according to this, mass can neither be created nor destroyed. According to this principle, the continuity equation is, we can take mass of the shaded area, or we can call it as a region also. Mass of shaded area or region, that is the density of the flow into the area into the time interval in which the fluid is crossing this part, this area. So this will be the mass. And when I talk about the mass flow, so how much mass flow flows on this body? So that is nothing but the mass and the rate at which the mass is flowing. So now we have our mass as rho into A into delta T by T. So m dot. So mass flow is denoted by m dot. This will be rho A into dt by T. So this is the continuity equation, and basically the equation is like this. So density into area into velocity is equal to, at the area 1 and density 1 and the velocity 1 is equal to the density of area and velocity at second body. So for this I would like to consider a nozzle. Okay, this is a small nozzle. It's a convergent nozzle. Let us say our flow is flowing with a velocity v1 at this point. This is my region 1 at this point, and the density of the fluid is ρ1, and the area of the duct is A1. So next, at the region 2, when it flows through it and comes out, that is, we call it as an outlet. So in this region we have the velocity of the flow as v2 and density as ρ2 and area will be A2. So according to the principle, applying the continuity equation according to the principle, we get ρ1 A1 V1 is equal to ρ2 A2 V2. Usually velocity will be given and the density of the flow, whether it may be a water or any liquid, it will be given, and the area depends upon the shape of the duct in which it is flowing. Usually we take it as 1 by 2 pi r square like this. So it depends what is the shape of the duct. So this is the continuity equation and it works on these principles. So let's move on to the next concept, that is momentum equation. So next is the momentum equations. So as the principle is there for the continuity equation, same the principle is there for momentum equations. So momentum equation, we have already learned these equations in fluid dynamics. So there are no other theories or anything related to these things. The same is there, but in depth in what we are having is this momentum equation works on the principle of Newton's second law. So we all know in our lower classes we have already gone through the Newton's second law, that is the force is equal to the rate of change of momentum of the body. So rate of change of momentum, So looking at the Newton's second law, we can frame out the momentum's equation. So basically it is mass into area. So just we'll apply this for a momentum equation of some fluid flow, so we can relate it to our aerodynamics. So the same thing I am using convergent divergent duct in which the mass of the flow is, let it be a m, and acceleration of the flow is a. So when it enters, this is, we have region 1 of inlet and this is region 2 which is outlet. So when it enters with a force and with a velocity of v, then it comes out at m2 with an acceleration of some acceleration a2, and this is what we have here. So I will replace the acceleration by in terms of velocity and the time. So m into dv by dt for a small amount of velocity at a small amount of interval of time. So this is what we can relate the momentum equation to the aerodynamics. And one more thing, this equation can also be written in the three-dimensional form. So continuity equation, momentum equation and energy equations we can write in three-dimensional form. I will let you know later, because there is a derivation involved in it, so we have to derive it for three-dimensional equations also. So this is how the momentum equation works. It is as simple as it is. And then let's move on to the energy equations. So the energy equation is this, in which energy equation, so same as we learned, the principle goes on the same. So what is this principle means? Energy can neither be created nor destroyed. So we all know this, energy can neither be created nor destroyed, but it is transferred from one system to another system. So we have to keep in mind when we are going through the energy equation, or we are applying the energy equation for some other task, we have to keep in mind whether the condition is closed or open, because when I am talking about an energy, we have a relation with the internal energy and the work done. when we look back to our thermodynamics, so there is a first law of thermodynamics which states that the relation of the energy, internal energy and the work done and heat transferred. So whenever we are using the energy equation, we have to keep in mind whether the system is closed or the system is open, or the surrounding, what is heat exchange taking place, whether it may be between the system and surrounding or between two systems. So these are all the conditions we have to keep in mind. And talking about the expression for the energy equation, so energy equation expression is as simple. So it is a heat internal energy E plus W, that is work done, and in the more precise sense we can call the term as enthalpy in this energy equation, but it is not as necessary because we are not dealing with the thermodynamics, we are just applying the theories to our aerodynamic purpose. So to the what extent we have to apply, then it's far enough. So let's move on to the next part. So these flows, when applied using the equations to the fluid flow, so how they works, what are the paths, and whether they go in a straight path or a steep path or some other path, if a body collides with another body, so what will happen. So all these questions I will answer in the next concept, that is we are going to deal with the path lines, straight lines and streamlines. So let's see them. So coming to the part called path lines and streamlines, so these are the important things you should keep in mind, but it will be helpful in aerodynamics, like to locate the path of an point or a body in the fluid flow. So path lines and streamlines. So what is this path line? So how you define it? So for this I have drawn the figure like this. So just go on to the figure. There is my element, here is my element called A, which is flowing through the fluid with a velocity V. Consider element A which is flowing in fluid with a velocity V, and this after some time, let's say interval of time called T, a small interval of time delta T, it comes to the point B. This is the B point and this is the A point. So after the time it passes through the flow and comes to a point B in a small time interval delta T. So this path, so this is what path is there, where A is translating from this path to this path, point A to point B. So this path is called a path line of A. We call it as path line of A. So this is the thing related to the path lines. And then this is a simple definition, just keep in mind, it will help when I use the path line word. Just keep in mind that some element is moving through a point and it reaches some point in interval T. So next I am using the word streamlines. So streamlines is also the same thing, but the difference is, let's say my body A, the same body, is moving from point small a to point B. So this is the path. So usually in path lines we call it as it is a path that the element A is traveling in an interval of time. So in this streamlines, when my body reaches a point B, if I draw a curve to this tangent which indicates the velocity vector of that point, velocity vector at that point. If this is the curve path line and if I draw a tangent to this, it indicates the velocity. So this velocity point, velocity vector, we call it as, in more precise way, velocity vector at that point. So what is the definition now for the streamlines? Streamlines are those lines in which when I draw a curve to the tangent, it gives the velocity vector at that point. So obviously there is a doubt, like this streamline, is it different for different velocities? So yes, obviously this is different for different velocity, because the velocity vector changes at each and every point on the line. So this is all about the streamlines. So another question is there, how to relate it in mathematical way. So in this mathematical way, if I try to apply my theory of streamlines to mathematical way, I would like to carve some equations which tells me how the streamline goes and how it works in aerodynamics. So let us see. For that, I am considering the same figure in which I am taking axis. So this is more obvious we likely to do in each and every derivation as concerned to the aerodynamics. We just draw and we just use the coordinates to make it more precise and very easy. So this is z axis, this is x, and this is y axis. So in this, when my body A goes from this, I just draw a velocity vector, and this gives the curl. Then I am using the concept called cross product here. So in lower class of mathematics, we have gone to the analytical geometry in which we have learnt the cross product or dot product. So in this, delta into V, this is the delta into V is equal to 0. So what this means, this is equation for streamlines. So how to understand this? So the cross product between the velocity vector and the moving path. So this is equal to 0 when the streamline is at rest or my body is at rest. So there will not be any movement. So there will not be any velocity. So it is 0. This is the mathematical relation for the streamline. Next we will move on to the cross product. Not cross product. We will move on to the part called circulation concept. Circulation concept. In this body, how it rotates in the path, whether it may be a path line or a streamline. So how the rotation movement takes place, if it rotates, and how it translates into the motion. And using this concept, we can generate the lift on the airfoil. So there is a concept called circulation which deals with the generation of lift on the airfoil. So how it generates. So let's see that. So guys, I hope this video was very helpful for your studies, and let's move on to the next concept in next video. That is, I am taking the circulation and the Kutto-Jokovic's theorems and so on. So if you are not subscribed, please subscribe to my channel called Officer Aerospy. Like, share, and press the bell icon for the notifications. So let's see in the next video. Officer Aerospy.